Well, so I'll just start with, it's been nice. I've been part of this NSF Quantum Leap Challenge Institute for Robust Quantum Simulation. And when we started, one of our goals of QSim, like our stated goal.
When you started, NSF was still a thing.
Yeah. Nathan's the worst straight man because he has to wait for the punchline. Because I was going to say the goal was that we wanted people to take over handling the conference. But now we need people to take over handling all of NSF. But thanks. Yeah. So if you want to talk about the doom, you can talk to me later. So we're here at Duke University. It was built in 1927 by tobacco barons who wanted to be European kings. And they built this nice cathedral to capture that. So when you think about quantum simulation, one thing is an interesting place is, for me as a chemist by training, is thinking about chemical dynamics. And so a lot of photochemistry, like the way we see this slide, the way we see this screen, the way that lights harvest energy, an electron is excited from its ground state to a highly excited state. It can hop around the molecule from place to place. And then the atoms or the nuclei will try to shift themselves to handle this big perturbation, because it's a huge perturbation. And so understanding how to calculate these things is a really important thing to understand not only nature, but also to build organic solar cells and all these other sort of things. So a common way to model it classically, in your physics class, say, is you have electronic states. They connect to bosonic operators, which capture the vibrations of these molecules. And that's it. And so this linear vibronic coupling model is widely used. And even in this simple model, it's pretty easy to write down parameters, which leads to a problem which is pretty hard to solve classically. So what's great is with our trapped ion system, we can simulate this model. We just map electronic states to qubits, vibrational modes to motional modes. And then if we have, and this only makes some sense in a chain of ions. And in that chain, what's nice is most qubits couple to almost all motional modes. They drop out of some. And you can also apply 2-qubit gates that connect qubits to qubits. All right, so my colleague David Beratan, who's in chemistry, he's in the National Academy for Chemistry. He spends most of his time thinking about these things like electron transfer in these molecules. And so working with him, we tried to figure out, is there a regime that we can aim for quantum advantage? And it was kind of interesting because it turned out to be the kind of intermediate coupling regime. So if the coupling is very weak, we have all kinds of simple methods we can use. If the coupling is very strong, it turns out that Ehrenfest still will work in that regime. And somewhere in the middle, where sort of the coupling to the vibrations is on the order of sort of the energy of these excitations, it does look like there's space for a non-error-corrected quantum simulator to actually do something which is very hard classically. And so that's what we're trying to do. We have not done, that's what we're trying to do. So I'm going to talk a tiny bit about trapped ions. So trapped ions are made out of, there's an ion. The ion basically has to have two kinds of transitions. It has one transition which scatters a lot of photons. We use that to laser cool the ion, and we use it to measure the ion. The other thing it needs is a transition which scatters no photons. And that transition is the transition we use for the qubit. So we use the qubit control to do all kinds of things. And then we use actually the Coulomb repulsion between these ions is the thing that creates the vibrational modes and allows us to do qubit gates. Now, we would love to have better traps. And so in this Nature Review of Materials, myself with Lincoln Labs and Hartmut Hefner at UC Berkeley, we wrote down all the things we'd love to have in better traps. So if you like people manufacturing traps, please get them to work for me. The way we do control at Duke, for most of our systems, we use ytterbium. Ytterbium's interesting. It has a hyperfine structure, 171 hyperfine structure. So it really has basically a qubit on the m=0 states, which makes it insensitive to magnetic fields, which is good for us. There's just a super lucky break with ytterbium, that the Raman laser is the same laser you use to cut masks that people use to make computer chips. So that laser is like a commodity, basically. They're always available for the power. They're relatively cheap. And it drives this Raman transition between these two states. The way we do 2-qubit gates, we can think about it starting with ion and then motion. And I have this picture from our friends at Innsbruck, because it captures when you have a long chain of ions, you actually have 3 n motional modes. Normally, your laser will see n or 2n of them. And if you park your laser so it drives the qubit, that's the black curve there, that carrier transition lets you do qubit control. The red and blue lines correspond to doing qubit control and either adding a phonon motion or removing a phonon motion. And that allows us to do something amazing, which is you can actually sideband cool these things to the ground state of motion. And that's what this plot is showing. So at the top is like what we see after Doppler cooling, which is the main laser cooling. And the second is what we see after we've removed all this motion. Okay. Now, when we do 2-qubit gates, the original 2-qubit gates by Sirac-Zoller required, the idea for 2-qubit gates by Sirac-Zoller required us to use that nonlinearity of having no red sidebands to transfer information between these different qubits. That gate worked after this gate worked, which was by Molmer and Sorensen. And what they realized is that if you drove the red sideband and the blue sideband, both detuned by the same amount, you end up with this pretty cool interference. And the interference gets rid of the dependence on n and allows you to basically create directly this Ising type of XX interaction. And that's the normal 2-qubit action we use all the time in ion traps. And then the thing which is a little more challenging than their original picture, and I do want to say, when this paper came out, there were really similar ideas by Solano and Milburn separately. So 3 people separately came up with this idea. But over time, we just call it Molmer-Sorensen gate. It's kind of a funny historical thing. So in these 5 normal modes, with 5 normal radial modes, we actually have to handle all of these modes. So the way we do that is we take advantage of like a really nice feature of oscillators. So an oscillator position and momentum operators, well, this is always true for all quantum mechanics, but position and momentum, they don't commute. But when they don't commute, they just give you a number. So in this particular Hamiltonian, what you see is there's like a spin operator multiplied by this a dagger k plus ak, which is just the motion or phase of the oscillator. The sigma part is all the same, so they commute with themselves. The only thing that doesn't commute is that position part. And as a result, if you do second order magnets expansion, it exactly converges. Like you don't, like it's a solvable time dependent Hamiltonian because the first commutator just gives you a number. I guess second commutator gives you a number. So when we do this, we get 2 pieces. One looks like a spin dependent displacement. The other part looks like the Ising kind of interaction that we would like to have. So my group, there are different ways to get these things to work with multiple modes. My student, James Lung, we investigated doing these frequency modulated gates. We spent 5 years making better frequency modulated gates, using machine learning, thinking about how to fix crosstalk, all these fun things. This is a paper from the results here from 2020. I really like this one because the orange curve, which is the motion being displaced and then coming back to the center, which is key for the gate, looks to me kind of like Smokey the Bear with a little hat. And the green one looks like a bee, and I like that. And the other 2 dots you see don't really do anything because they're pretty far off resonant. So we spent tons of time making sure to always put the motion back to the center because we're doing qubit-based quantum computing, and I never want to see that motion. Now the point is, you don't have to do that. Here's a picture of me and my nephew at the playground. So you can keep putting energy into the swing, move further out in motion state. It's not good for qubit-based quantum computing, but it allows us to control the motion. So now we use that to apply it to quantum simulation. And the first thing we looked at was this idea of conical intersections. So again, when you photoexcite a molecule, the electron's excited, it has to get back to the ground state some way. It can reconfigure. And sometimes you get this, this cone crossing. It's kind of like a Dirac cone, but instead of being in momentum space, it's in position space. And the electron will crash down through that, and you get all kinds of products. And actually, that is how your eye works. So all of us are constantly going through this conical intersection while we're speaking. What's cool is people have all kinds of evidence from experiments looking at these different photo-driven reactions. This one, there's actually 2 canonical intersections from the reactants to the products. So I've always been interested in this question of, what about the quantum stuff? And so one cool quantum thing is there should be a geometric phase on this ground state. And people in the 1990s doing femtosecond spectroscopy, these theorists were like, hey, I want you to go to lab, and what you're going to see is a decaying cosine with wiggles, and that is going to show us that there's this phase. And then on the bottom is the plot of what they would like to see if you could actually look at the wave function. And in the end, this experiment never happened. Timing is challenging, orientation of molecules is all over the place. It just never happened. So what's the simplest canonical intersection you could imagine? It's actually just 2 oscillators. So you can think of it as a 2-dimensional harmonic oscillator. And then you generate a spin-dependent force. And that pulls you can think of it as pulling the oscillator out into this ring. And then you see exactly this cone. And this is great because it maps very nicely to ion trap Hamiltonian, which was pointed out in this chemical science paper by Ivan Kassel's group at UNSW. When that paper came out, my students were very mad at me because we were already working on this, and I told them we shouldn't publish a theory paper, but that's fine. I think they've forgiven me. They all have jobs. OK, so the basic idea that our approach was you start in the 2-dimensional harmonic oscillator, and then we trotterize the application of this force. And the reason why we use trotter here is actually because we want to, it helps us keep the intensity of the lasers equal. Because the intensity is the same, and we're only changing phases. So we trotterize, and as we do that, what should happen is this circle, which is the ground state of the 2-dimensional harmonic oscillator in position space, should become the C. If there is no conical intersection, you should just see a donut. And if there is a conical intersection, you'll see the C. And if you have a tiny bit of Z field, which splits the conical intersection, the C should rotate if it's constant over time. So we did this. We did it using 5 ions. We used 5 ions because the other part of the group at the time was making a control X gate on a 5-ion quantum computer. And so we weren't going to dump out other ions to go back and forth. We just worked with this. It actually had a nice feature, which is we defined the 5th mode and the 3rd mode as our 2 modes of interest. We chose the electron. The electron, the vibrations it talks to is 5 and 3. We picked the center atom because it doesn't interact with 4 and 2, which I know this is a lot of experimental details for this crowd, but it actually prevents crosstalk to those other motion. And then we read out, and this is another nice thing, is we can read out the amplitudes of these motion without having to go back to the electron. So what's nice is so you can see the nice theory next to the experiment, looks good. We look at these cross sections, it looks good. That's the plot above is the one that's in this Nature chemistry paper. The one below is not in the paper or any of the appendices. We could see this thing all the time. Sometimes we had better contrast. Sometimes we really had the alignment perfectly fixed. It was quite nice. So this got me more excited about going and really pushing these spin motion things. So I just want to say these students who worked on this are all gone. Gloria and Bi-Chen, they moved on to do neutral atoms. That's OK. Chao and Ye are still doing ions. That's great. Jacob also doing ions, and this is the Jung-Sun Kim. And I didn't talk about it, but using these same tricks, we're actually able to make entangled states of motion. So Gloria and Jacob were really the drivers of these 2 things. And then at the end, Gloria focused on making entangled states across all these motional states, and Jacob did the conical intersection. The other thing which I think is great about, I think the other thing which is great about quantum computing ion traps is that you can verify and validate by looking at other things. And so our friends in Sydney also saw this conical intersection. Their experiment is slightly different in that they looked at the dynamics. They really wanted to see how the wave packet moved in time. It's also different in that it involves a single ion. And so these two modes are like two real physical modes. And the lasers are applied at the same time because they're just running at the same time. So this is more like a really direct simulation. I think ours is a little more, right, we pick from sets of modes obscured. And these guys have been doing really great work since then. There's a nice paper in JAX, which is the best chemistry magazine, where they just showed chemical dynamics building off this paper. So please check that out. OK. Now, other thing about nature is also an open quantum system. So it would be great if we could think about all these things that the chemists care about. They actually don't care about in vacuum. They care about it when it's in its environment and it's dissipating energy out to the outside. So they're in ion trapping. Dissipating on the motion is pretty easy. You just have some ion which isn't part of the quantum information, and you just cool it. Like I said, we can sideband cool. So we just spend some time sideband cooling it. And that allows us to basically add on this Lindblad operator, which cools. The goal is you want to try to target these spectral densities that people can measure. So on this plot from the Physical Review letter, the blue is the real spectral density, which has tons of little peaks. And you see it's kind of captured by about 5 Lorentzians. And so we want to make the spectral density over this continuous set of modes, which has the correct Lorentzian space for these different J's. And then we can ideally capture the whole system. Now, you might say, well, Ken, you only have n modes in your ion trap. And now you want to somehow capture an infinite number of modes represented by this integral. Well, there's this really nice paper from Plenio's group, which basically says it's no problem. And what it says is if I have anything which has this continuous set of modes and I have something which has only this one mode, I can tune the damping of that single mode such that the 2-point Bath correlation function is the same. Now, it's not exactly the same, right? In some sense, the observables are different. When I look at the dynamics of the spin is the same. And that's the dynamics that I'm actually following. So that's really, really quite nice. OK, bad news is when we were, not bad news, but when we were starting this, we did not have access to this damping in a way that wouldn't destroy the rest of the system. We just had dephasing. And damping and dephasing are very different. So on a qubit level, you can think of damping as like T1 type noise and dephasing as the T2 type noise. But what then is remarkable is the 2-point Bath correlation functions are the same. So even though like damping and dephasing are ridiculously different things, somehow dephasing, if I just look at the 2-point correlation function, gives me the same result. So, so what we can do is we basically take advantage of this. We're going to do spin dynamics. We know the 2-point correlation function is the same. The Spin-Boson model we're looking at is Gaussian with this quadratic term. Damping is also Gaussian. Life is great. Dephasing is actually non-Gaussian. And that means actually the higher order correlation functions are not going to agree. It also means that our classical simulators are going to have a harder time. So that, as long as we're kind of like weak spin Bath, we can basically use these dephasing models instead of having to worry too much about damping. So then Ke and Mingyu and Hangai went to work on this. Can we actually create these spectral densities we want just by looking at dephasing? We added a couple ions to this experiment, so now there are 7 ions in the trap. This experiment is a 1-ion experiment. But again, we're doing other stuff, so we just run it on the same experiment. The basic idea is when we do these kicks, yeah, so back to the swing set analogy, right? Yeah, I guess I was the older brother. You know how it is. So my younger brother's on the swing, and I should be pushing him higher and higher, but then I push him at the wrong time, out of phase, kick him around randomly. Just what it's like to be an older brother. It's kind of your job, I think. So we can use that same thing in 2 places. If we use it at the beginning, it actually allows us to move from this very pure motional state to heat it to any thermal state. We use it, the second part is actually as a way to control the dephasing or the T2 of these oscillators. And so by randomly controlling those two things, we can control this. And so this just came out in Nature Communications, and it's collaboration by myself, David Baratan, who I mentioned, and Jung-Sung Kim. Yeah, and then of course, everybody's moved to Berkeley. OK. So what's nice is on the one side, you can see that we can tune the bath's initial temperature. You see the fuzzy part, which is the experiment data with error bars. And then the line is the theory. Looks great. We can tune the bath's spectral line width. That one I think is pretty neat because you can see first like this sort of echo of the bath coming back to talk to the spin, damps and goes away. And with that actually comes a flip in the phase of the later oscillations. So we can go from underdamped, overdamped, work through these things. And again, just by changing how we're randomly applying these things, we can change the width of this spectral density. So of course, our goal is to have a more complicated thing than a single Lorentzian. So in this case, imagine you have the shape up top is the spectral density you want. I will say this, the units on this are interesting, because these units are the units of the physical system we would like to look at. So the physical system we would like to look at, its dynamics happens on the femtosecond timescale. The spectral densities are on these wave numbers. So like one wave number is 30 gigahertz, in case you don't know. But in our experiment, what happens is all of these things happen at megahertz. And the kind of time scales that we're talking about are like between megahertz and kilohertz. Even though we don't control where the we don't control, it's not quite right. But anyway, we have an ion string. Ion string has modes. Those modes have some frequency. However, in this spectral density, the place we put the Lorentzians depends on the detuning from those lines. So we can control up to the detuning where these different lines are. And that allows us to build this shape. And then here at the bottom, you see, again, we run the experiment. The theory matches the experiment. We can look at 2 modes, 3 modes. It's pretty good. So then we worked a little bit on a stretch goal of like, well, what if we wanted to do something that physicists are more interested in? Like, let's try to look at ohmic baths, superohmic baths, these sort of things. And the problem is right now, given just a single mode, we can only cover a small part of that band. But you can see in the green and orange and blue dashed lines, those are these spectral densities with a power law. And then we, over the region where the qubit is resonant, we try to match those things, which we can do. And again, we see pretty nice results, matching the theory and the experiment. We looked at vibrational assisted energy transfer. I want to point out that the first vibrational assisted energy transfer experiment was done by Hartmut Hefner's group at UC Berkeley back in 2016. Quite nice experiment. I usually have a slide on it, but I cut it out when I was cutting slides. So my apologies to Hartmut. So what you see is you want the electron to hop from A to B. But when it's not resonant, it has to borrow a phonon or many phonons. But it can borrow more than one. So the orange line is where the phonon is way off resonant. And then the hopping doesn't happen. So the orange line stays at top. The green and blue lines are different subharmonics, which allow it to hop. And you can see that hopping there. You see that if you turn up the temperature of the bath, this vibrationally assisted energy transfer washes out. And then at the bottom, you see this, finally, the limit of using a T2 process for a T1 process. So the blue, orange, and green lines, the solid line is what you would have if you had a real T1 process. We just have this T2 process. So the T2 process leads to the dashed lines. Our experiments match the real error. But what you see is as long as you're in like weak coupling or short time scales, that T2, I don't know. The T2 masquerading as a T1 process works really quite well. And here it breaks down because we basically keep turning up the strength of the coupling until it breaks down. This work came out on the archive near the same time as really nice work from Guido Pagano's group at Rice University, which is now published in Science Advances. So is in the audience. So if you have more questions about that, you should hunt him down. And it's cool. So now we have both the ability to think about this tunable dissipation and tunable dephasing. So just thinking forward, I think there's actually in this bosons are like an interesting way to aim for advantage outside of qubit space because the Hilbert space of one boson is infinitely large. Now you're not going to control that infinitely large space. You're going to control some amount. But what we found when we were looking at our classical simulations with David Berretan is that you're basically, if you're trying to build a tensor network simulator, at the beginning of the experiment, life's good, life's good. And then as you go out in time, that infinite dimensional space is just making the bond dimensions of this tensor network bigger and bigger and bigger until it basically crashes. It basically no longer becomes reasonable. So I believe there's an opportunity to try to look at long time scale dynamics where actually qualitatively the quantum computer will give you better, quantum simulator will give you better results than a classical simulator. So this really nice work talks about how to do it in terms of superconducting qubits and using their bosons and things. And there's a similar nice work by ions. I think there's just a lot of opportunities for fermions, bosons, gauges, et cetera. This is just one other example I wanted to highlight from Elena Green, Christina Mushik, and Norbert Linke, where they actually just use the bosons as a way to generate heat. So you'd like to do some kind of, you'd like to make a not pure state simulation. You'd like to have some density operator. That density operator, you use it by basically entangling into these bosons, which are just floating around. And then you fake these thermal states. So it's really quite good, I think. So just to quickly conclude, I think there's a lot of really amazing things one can do by putting together these ions and modes. And I think it is kind of a shortcut for thinking about doing quantum simulation, which maybe beats classical computers in a really qualitative way, instead of compared to other ways one could think about beating them. I think that we can build up to systems which should be of the time scale of this photosynthetic system with all of its vibrations, or not all its vibrations, with its key vibrations. I will say I had always been hesitant in starting this path because in our experiments, when we do 2-qubit gates, for a long time our main error was motional dephasing. But then when we did the experiments with Ke and Mingyu, and Mingyu is also here, you can hassle him about that, is we found we always had to add dephasing. If we wanted to get close to like a real physical system, our background dephasing doesn't matter. Now it'll start to come in as I try to have more modes, but that I think is pretty solid. And then this last bit, I thought about adding it, but I realized it wouldn't be enough time. Is just thinking about the difference in T1 and T2 has allowed us to kind of discover a different kind of phase transition where you can think of it as your noise going from Gaussian to non-Gaussian. So in the quantum Rabi model, in the dissipative quantum Rabi model, there's this quantum phase transition. And we see that where it happens changes as you add non-Gaussian noise. But there's also like a real qualitative difference having to do with higher order moments of the motional operators. So please take a look at that. So that I'll just say thanks to all these nice funding agencies, which I hope last forever. Thanks to my group. And yeah, we work on a bunch of things. And then also I'll just flash out that we have Duke Quantum Center. We have tons of people working on all kinds of quantum simulations from chemistry like myself to nuclear physics like Natalie. And currently we are working on a National Quantum Virtual Lab to build an academic ion trap quantum computing system, which will have some of these spin boson capabilities for everyone to use. Don't get too excited, because our current plan is to build the first one in basically 2030. So just get ready for it. All right, thank you.
Excellent. Ken left plenty of time for questions. So questions from the audience.
Thank you. I have a question regarding one of the integrals that you were mentioning about one specific experiment.
Yeah.
Maybe I missed something. Where the experiment directly was in the time domain and you do a Fourier transform to the frequency domain, because the integrals were integrating over the frequency.
Yeah, that's right. So the so we have a spectral density, and then we have some integral over that spectral density, say with some bosonic operators, which are also infinite, right? Mm-hmm. So we map this following work from Plinio to discrete operators. And this discrete operator well, yes, let me make this plus AW. So how to capture this with these discrete operators requires us to add some Lindbladian term. And so we add our dephasing term, which mathematically makes this this. So then we just work in the time domain.
Okay,
Does that
great.
make sense?
Yes. Yeah. Thank you.
Further questions?
You'll have to forgive me if I don't know that much about boson simulation yet. But you mentioned this work from Plano, which seems very interesting, about like mapping these infinite level bosonic systems to some finite dimensional system. And this seems very useful for obvious reasons. And then you mentioned later in the talk that you think these bosonic systems might be resistant to classical simulation, particular quantum tensor network simulation, because of increased bond dimension, because of these large systems. So what I'm wondering is, can this mapping provided by Plano, I think that was his name, be used on like tensor network simulators? And would that possibly increase the reach of classical simulators? I hope that makes sense.
No, that does make sense. Okay, so first off, this is my cheap analogy I have in my head. So if you don't like it, don't make fun of me. If you think about like just an atom emitting a photon, it looks like some A term, right? Sigma minus A. And then the reason why we have like a decay constant is that I basically integrate this over some spectral width. And so that's my simple idea of somehow an infinite number of oscillators is equivalent to some discrete thing which is being damped. And that's Plenio's observation. Now, Plenio's observation works because everything is Gaussian. And so the 2-point correlation function is enough. So from Vadim's talk, I thought that part was actually pretty, spoke to me a lot, which is I don't know why the fourth order correlator is so much harder. I mean, Vadim did a great job explaining why the fourth order correlator is much harder than the second order correlator. But somehow the same thing happens here when I move to non-Gaussian noise. That non-Gaussian noise, like our usual perturbative tricks, fall apart. So in later work by the same author, Plenio, they have a thing called, the acronym's DAMP-F, which is like dissipative, whatever A is, matrix product formulation. And that's the thing we've been trying to compare against. That's very efficient. It's polynomial. But it looks like we can get to system sizes where, like in real time and real space, we can go to larger distances. Yeah, so you can look that up as well. I'll write it down, DAMP-F. Hi, Brigitte.
Hi. So my question is,
You're off.
oh, I turned it off, sorry. It's on now, right?
Yes.
So do you think you might be able to simulate like one decade of 1 over F noise? Spectral density?
Yeah. I think we can, yeah.
Oh, that's cool.
Yeah, so I'm kind of, I mean, my aim in the next couple of years is to get to sort of 10 ions with 10 modes.
Yeah.
And I think with 10 modes, we can actually get a decade
You
of
need
these
only-
Lorentzians together.
You need only 5 for 1 decade. We studied that a long time
Yeah,
ago.
so then we can do 2 decades. Great.
All right. We can do with it.
Wonderful. Wonderful. Thank you very much. Let's thank the speaker one more time.